Running the experiment is only half the battle. To prove your CO2 reduction was successful, you must analyze 3 performance metrics. First, activity. How fast is the reaction occurring? Second, selectivity. What percentage of our energy actually made fuel, instead of waste? And third, stability. How long does our catalyst last before dying? The potentiostat provides our electrical data. The most common diagnostic test is LSV, or Linear Sweep Voltammetry. By scanning the voltage, we find the onset potential, the exact moment the reaction starts. If we run a baseline scan in argon gas and compare it to a CO2 scan, a clear difference proves our catalyst is actively reducing carbon. Once we find the best voltage, we use chronoamperometry, or CA. This holds the voltage steady for hours, acting as an endurance test, while we collect the final products. But electricity alone doesn't tell us what chemicals we made. For that, we need external detectors. For gas products flowing out of the cell, like carbon monoxide or methane, we use gas chromatography, or GC. Different gases travel at different speeds, creating distinct peaks on a graph. For liquid products trapped in the water, like formate or ethanol, we use nuclear magnetic resonance, or NMR. This uses magnetic fields to identify specific carbon-hydrogen bonds, giving us the exact concentration of our liquid fuels. When comparing catalysts, looking at raw current is misleading. A massive sheet of copper will naturally pass more current than a tiny wire. To level the playing field, we divide the total current by the geometric surface area of the electrode. This gives us current density, measured in milliamps per square centimeter. This is the true measure of a catalyst's activity. Finally, we calculate the most critical metric in the field, Faradaic efficiency. This tells us the percentage of electrons that successfully created our target product, versus the electrons wasted on side reactions, like hydrogen evolution. By taking the moles of product found in our GC or NMR, multiplying it by the electrons required per molecule, and dividing by the total electrical charge passed, we get our final efficiency percentage. A high Faradaic efficiency means you have a highly selective and highly successful catalyst.